GAG, and we're actually going to look at the bonding that's involved. And so the material is going to be like silly putty, but that's different from GAG because the silly putty has silicates in it. So for the lab activity, goggles, lab coat, or apron and gloves, because borax can aggravate the skin and the eyes. And these are the materials that you need, but pause to get the exact ones, but you're reacting a borax solution with PVA glue. And what you're going to be asked to do is to record your observations. You're going to start off by marking your cup the same way as the pre-marked one is, but leave that for other folk. And you're going to, in that cup, put 4 ounces of the glue, about a 1/4 cup of water and mixed well, and add some cornstarch, which sometimes just helps with the texture, and optional you can add some food colouring. Then you're going to measure out the borax, a small graduated cylinder, and you're going to pour half of that into the glue water mix. And if it's runny, don't add all the other half, and make sure you write down what has happened to the mixture and how have the reactants changed as you're forming the products. And if you're not going to do the test activities right away, pop your GAG into a Ziploc bag and make sure you have described the appearance of the reactants before and what you've produced. Now, tests you're going to do are the following there, and comment on what happens to your one. And it says, if careful, you can pull it into a thin film. Now pull it sharply. Pour the material from its container by tipping the container very slightly. And then if you tip it very slightly backwards, you'll see what happens. Now, we want to look at the bonding in the reactants. So you've got sodium borate, metal, non-metal, water, what are the elements that are involved, and ditto with the polymers at the bottom. And so you can just check out here what you've got. It's all about the type of atom that's present, shared electrons in a covalent bond, donated, received electrons in the ionic bond. And so what are the intermolecular forces? So in the ionic borax solution, you're going to have electrostatic attraction between the ions, attraction between the positive cations and the negative anions. Now, water is covalent, but because of the different electronegativities of the hydrogen and oxygen, you end up with a polar covalent bond. And in this case, it's a hydrogen bond, because hydrogen is bonded here to oxygen. You'd also get a hydrogen bond if it's bonded to nitrogen or fluorine. And in your PVA glue, you've got carbon, hydrogen, oxygen, a hydrogen bond between one polyvinyl alcohol molecule and another one. And between the carbon-hydrogen part, there might be some temporary dipole London dispersion forces, weak ones. And so what we're going to do, we're going to describe what's happening, looking here at the PVA molecule, but we're just going to represent it by a red blob with the connectors. And so in the polymer, you've got lots of those PVA monomer units joined together. And here we've got how we're going to represent borate with a blue rectangle. So it's that BOH4 minus ion represented by the rectangle. So put them together Got to remember that we've got separation of charges because of electronegativities, and the same thing happens with the borates, OHs, but it's going to be the oxygen on the borate and the hydrogen on the OH of the PVA that are going to link together. So borate's going to have the delta negatives, and the PVA, you'll see, has the delta positive. And for the PVA, each glue monomer has 3 polar OH groups, but the hydrogens from 2 of the OH groups bond to one borate above and below the borate, because you've only got 4 delta negatives. And so we can make it much more complicated here, showing 2 polymer chains of PVA above and below the separate borate anions, which are cross-linking the borate with the PVA and making hydrogen bonds in all cases. A neat little activity that you can do if you've got materials available, beads, thin string, cotton, make a string of beads tied at the end so they won't fall off, and place the 2 strings in a cup and pour them out and see what happens. Now, with the 2 strings, join them together with our pretend cross-linking baggy ties with the thin wire inside. Then just put that back in and tip it out and see what's going to happen. Now, what we want to do, we want to try and explain in terms of those hydrogen bonds that are formed, what happens with the test that you've done. The low stress, pulling it very gently, it flows. Are you breaking those hydrogen bonds or not? And go through each of those items there in terms of the cross-linking to describe in terms of intermolecular forces between the glue molecule polymer and the borate. We also need to write explanations and what we want, the conclusion to this activity. Explain the changes that occurred to the materials during the reaction and why. Define a hydrogen bond. Add a drawing, a simple cartoon showing one borate ion bonded to 2 parts of a polyvinyl alcohol glue chain. And on your picture, clearly circle where the hydrogen bonds are, because that's what we're looking at here. And as an aside, the borax, here's one of the brands called 20-multein borax, because borax was extracted from Death Valley, Nevada, and what they used to do was have these 20 mules pulling these enormous carts to get it to market. And then summary. Now, these are molecular bonds, intramolecular or ionic here, which isn't molecular. So these are what make up the PVA or what make up the borate, sodium borate, and the properties. You can pause that and review and look at them. And then we can look at the intermolecular forces. So these are between the borate anion and between the PVA, the 2 units. And here's a hydrogen bond, dipole-dipole, London dispersion forces, and the other force, which we haven't got here, is a dipole ion force, which isn't really intermolecular. And as a reminder, here's a periodic table with electronegativities listed, so you can just see the difference in oxygen compared to hydrogen, and indeed fluorine compared to hydrogen, etc. And interesting little things, Apollo 8 astronauts in 1968 took some silly putty with them. They were the first humans to leave Earth's gravitational field and to travel to the moon. Didn't land, just for a flyby. And they took some silly putty. One source says as a relaxation, but they actually ended up using it to secure tools in their near weightless microgravity. And then shuttle discovery in 2007, which took off to take the Harmony module to the International Space Station, and that had been named by Brown Academy students in Alexandria, Virginia, in a competition that was set up to name the module. But they also took a putty-like material. It's not silly putty, but we're looking at space connections here, as a heat shield repair tool. So repairing the tiles, and they used something like a space cork gun to put it on. And the plan was to experiment with it and leave it in the cargo bay and see what happened to it on its return. And finally, we're going to look at a school-generated experiment on the International Space Station, and to compare what happens to silly putty made on the ISS and its properties compared to a same product made the same day on Earth. And so the students said, what is the effect of microgravity on the formation of silly putty, and how do the characteristics of that silly putty differ from silly putty made on Earth? And to think about, what experiment would you like to perform in microgravity on the ISS?